Well, let's go ahead and get started. My name's Grant Cardon. I'm the Extension Soil Specialist at Utah State University. I deal with all things dirt. We're going to talk about soil salinity today and some of the aspects. We have Dr. Melanie Stock, who will also be participating in this half of our session. She's right there waving at you. Dr. Stock is our extension, urban and small farms extension specialist. And so she's going to actually follow up with my talks on what are appropriate choices of fertilizers and fertility amendments in soils in our saline and alkaline soils here in the Western US. And then we'll take a little bit of a break for Q&A and then get into the water session. And I'll let Neil Allen and Mike Pace, our additional speakers in that session, introduce themselves as we go along. But without further ado, let's get into soil salinity and pH. What are they, and why and how do we measure them? There's probably, well, maybe about 2/3 of the questions I answer deal with soil management issues in Western US soils that are a result of both high salinity and high pH. And so let's talk a little bit about what they are and why we're interested in them. Salinity refers to the concentration of soluble salts and soluble mineral ions, particularly in soil solutions. As minerals in our parent materials, the rock and the sand and the silt and so forth begin to weather and break down over time, they release their constituent ions into the soil solution, positively charged or cations and negatively charged species or anions. And so what we end up getting is something that looks a little bit like this. We have a number of different common salts that are in our apparent materials. We have gypsum, which is one that everybody is pretty familiar with. It's calcium sulfate. We have others as well, as you see listed there. And because we're in an arid or semi-arid area, over time, as these have dissolved and water has gone out of the soil solution over time, they've accumulated to higher and higher concentrations. One of the things I want to point out here on this particular slide is as these solid materials, and hopefully you can see my mouse pointer, as these solid materials here begin to dissolve and release their constituent ions, these are the individual atoms, the ionized atoms of the different elements. And so you have a sodium ion and a chloride ion and a potassium ion and so forth that are the atoms, the basic atoms of those minerals. And so I want to make sure that you understand these are the basic building blocks of matter, and they can neither be created nor destroyed. And so we're going to talk a little bit about that. Keep that in mind as we get to the remediation of this and managing for these materials in our soil solutions. So like I said, as over time, as water is evaporated from the soil or transpired, that's the use of water by plants from the system, ions begin to concentrate, especially in our arid and semi-arid areas in the Western US and throughout the world. You'll find these in Mediterranean climates, in desert climates, all over the world. Another thing I want to point out is that not only are these ions charged either positively or negatively, but so is water. Water has both a positive and a negative charge on them. And so one of the reasons why we're interested in lots of salt dissolved in the water in the soil is that excessive solute concentrations can interact electrostatically, magnetically with the water molecules in the system, and it reduces that water's free energy or the ability of that water to move around or to be able to move across a root membrane and into a plant. And so what happens over time is we get an accumulation of salt in our soil solutions. We can actually have a restriction of water uptake by a plant, which we actually call a chemical drought. So let's talk about what that means here. This would be kind of a diagrammatic expression of a typical soil solution with a root interface here. We've got dissolved ions in solution, and then we have water molecules, H2O, two little hydrogens and an oxygen there combined in a molecule of water. And in a normal condition, there's lots of water and there's lots of dissolved mineral content in that water. And there's enough opportunity in a low concentration situation for both water and nutrients to easily be delivered to the root surface and taken up by the plant and into the plant and used by the plant. But as concentration of dissolved salts begins to accumulate, there's a lot of interactions, magnetic interactions going on between water molecules and surrounding salt ions in solution. And that again reduces the ability of that water not only to move freely through the system, but to actually be able to cross the root membrane. It's harder for the plant to pull water away from those interactions and into the root and up into the shoot as it's needed. And so when we see a chemical drought occurring, what do we see? We see symptoms of what would look like water deficit or water stress being expressed in stunting, reduced vigor, telltale wilting that you would normally see in a water stressed condition. And then if we get more and more accumulation, we'll see things like the burning or browning of leaf margins. And in intense situations with like really high salt, you'll actually see the death of those tissues toward the margins of the leaf. And so this is very typical of what we would see in a fairly advanced salt injury condition. Not only do we have the stunting and wilting, but you get this what we call marginal burning or necrosis, death of the tissue on the outside edges of the leaves. Here you see strawberry and squash and other things and fruit trees and what have you. So that's the expression that we often see. And a lot of times these symptoms will be mistaken for nutrient deficiencies. Even before we see the physical expression of symptoms in terms of leaf margin burn and other things, the wilting and stunting might be misunderstood as the need for water. But we can have situations where we have lots of water, plenty of water in the soil under normal conditions, but there's so much salt dissolved in that water that it makes it very difficult for the plant to pull that water away from those interactions and across the root membrane and into the shoot. And so long before we see maybe expressions of severe salt injury, we're already into levels of salinity sometimes that can reduce the vigor of the plant, much like water stress would over time. So how do we actually kind of get a handle on how much we have, and is it a level of concern in our soil at any given location or moment? So we said that salinity refers to the concentration of soluble minerals in solution, but we don't really measure it that way. It's difficult to go in and actually draw out the individual ions and measure how much is actually there. But we can use a surrogate measure very conveniently called the electrical conductivity. A simple conductivity meter can be used to measure the salt content. The reason for that is that because these are charged ions in solution, they will readily conduct electricity. I think you've probably all been told at one point or another by a mother or a watchful aunt or someone else that you're not supposed to be in the swimming pool when a lightning storm comes. Well, if you were in pure water, you'd actually be pretty safe because pure water is a pretty good insulator. But the fact that you're in a swimming pool with lots of chlorine, salts, and other things dissolved in the water, you've got a lot of these little charged ions in solution, which conduct electricity rather readily. And so you're in in a situation where you probably need to get out of that water in an electrical storm. But that's the reason why we can use conductivity as a surrogate measure for how much ion we have dissolved in that soil solution. And the more ion we have dissolved in the solution, the higher the conductivity of electricity through that medium. So we use electrical conductivity as a surrogate for how much salt is dissolved in soil solutions. If we take a look at that, then all of the literature that's been developed to categorize the response of various plants to levels of salinity in soil, we call it plant salt tolerance, is based on the electrical conductivity, or the EC, of that particular soil solution. Most plants can tolerate a fair amount, a little bit anyway, of salt in solutions without causing any difficulty with water uptake and other things, or damage to the leaf tissue. But once we get beyond the threshold values, the point at which they're okay, then they begin to decrease in productivity with increasing amounts of dissolved ion in solution. A lot of the things that we in this particular conference setting are interested in, fruits and vegetables and ornamentals and flowers and other things, tend to be fairly sensitive to salt dissolved in soil solutions. So their threshold values are fairly low, ECs of maybe 1 or 1.5 or so. And they fall off in productivity quite quickly as we have increases in salinity. So we do a lot of testing of various plants and not only the species, but cultivars within species and things like that, to develop this plant salt tolerance, to know which species and which varieties or cultivars within a species are more tolerant and more able to handle the kinds of conditions we have in our local soils. This is a good example of work we've done in the past with strawberries in terms of screening the tolerance to salinity. You see increasing EC, meaning more and more salt dissolved in the soil solution, and increasing injury to the plant tissue going up on the y-axis here. So we can screen for and monitor or learn from this what plants do better in certain situations, and that's the kind of thing you see expressed here in the table. So there are documents available in extension to categorize all of the different plants we might be interested in terms of their tolerance to various levels of salinity. And when you get a soil test, a routine soil test, soluble salts and salinity are one of the very first things that are measured on that and part of a basic routine soil test. Then we can, monitor for how quickly they also decline with increasing amounts of salt. We can also then look at the prediction of how a particular water that we're using, an irrigation water, a well water, a tap water, or whatever, might influence then the overall salinity of the soil over time. And I'm not going to go into a lot of detail here, but you can see that we can look at the applied water, and based on how wet the system is kept, this would be almost exactly what the plant needs. This LF.1, that's a leaching fraction of only 10%. You can see that an EC of the water will increase in that setting maybe 2 to 3 times in the soil what it was in the water itself. And so we use irrigation water EC as a precursor to what the soil electrical conductivity is going to be. And we can also produce or predict what the hazard of a given water will be in any situation to plant growth. So that's it for basics of salinity, why we're concerned about it and so forth. And we'll answer questions as we go along here a little bit. But I wanted to kind of direct a little more attention then to kind of a companion, at least in our soils, with salinity, and that's pH. pH of our soils, it refers to the activity or the concentration roughly of hydrogen ion in solution. You've heard of terms of acidity and alkalinity, and these refer to the activities of hydrogen in our soil systems. The more hydrogen, free hydrogen that we have in the system, the more acidic the system is. And the less hydrogen, more hydroxide that we have in the system, then the more basic or alkaline the condition will be, or the soil will be. I don't want to go into a lot of gory chemistry detail, but we measure pH as the log of the hydrogen activity. So we get a value somewhere between 1 and 14, with 7 being right in the middle of that scale. And the reason that is the case is that we use water as a reference. Water is kind of the basis for all life on this planet, and it turns out to be our reference medium for pH. Remember that water is H2O, or 1 hydrogen and 1 hydroxide unit in that molecule, 2 hydrogens and an oxygen. So a small amount of water splits, and so then you get half in hydrogen and half in hydroxide. You get a balance between the two. And it turns out that the activity of hydrogen in that case has a log of about 7. And so that's why we say that 7 is neutral. That's a pure water condition. Below 7, the system is acidic. Above 7, the system is alkaline or basic. When we talk about, because it's on a log scale, a lot of times we think, well, you know, my soil's 7 or it's 8. What does that mean? Above 7 or below 7, depending, with each whole number increment, it's an additional 10 times more or less hydrogen activity. So if we look at the scale, excuse me, if we look at the pH scale, 7 is neutral. Everything below 7 is acidic, and everything above 7 is alkaline. And each whole number increment is another 10-fold increase. So if we're at 7 and we move to 8, that's 10 times less hydrogen activity or more hydroxide activity. Again, we go to 9, that's 10 times more, or 100 times over what the neutral condition was. 10 would be 1,000 times, 11, 10,000 times, and so forth. So you can see that we get exponentially increasing amounts of hydrogen activity on the acidic side, and less and less on the alkaline side. So these aren't just simple numeric changes, linear changes. They are logarithmic changes. We get orders of magnitude difference between each whole number increment there. And to put that more in perspective, I love this particular graphic that kind of compares common things that we encounter every day with levels of pH on this particular scale. So we said water is kind of our reference for neutral. So water is right there in the middle at 7. Milk's a little bit more acidic. In this case, 10 times more acidic than water. Coffee, 100 times more acidic than water. Tomato juice, or tomatoes, raw tomatoes and things with the acids in them, another 10-fold increase above that. And so we're getting way out here. Stomach acid would be, if you work it all out, 1,000,000 times more acidic than water. So that's where we're at with that. And then on the other side, most of our bodily fluids are just slightly alkaline, like blood and tears and other things. Baking soda is another order of magnitude higher, or 100 times more basic than water. Your good old Tums and Rolaids and other things are another 10 times more basic than that, and so forth. We get all the way up here to drain cleaner. We get into the extremes of acidic condition, or even in basic condition, and these are either caustic or corrosive conditions, where we would see problems with skin burn or metal dissolution or other things. In fact, that's why we're interested in pH in the first place in our systems. pH controls solubility because of the activity of hydrogen or hydroxide in the system. Some minerals are more soluble in acidic conditions, and some minerals are more soluble in basic conditions. And so when we're talking about high pH, above 7, which is our condition typically in the Western US and Mediterranean climates, we're talking about an alkaline condition. Don't confuse that with the term alkali. That's a very archaic term referring to salts in soil solutions. And so there's some confusion sometimes in that. If you want to talk about salt, let's talk about salinity. If you want to talk about pH, we're talking about acidity or alkalinity in that case, okay? And again, this is just a quick, we're not going to get into a lot of detail till later when we talk about why or how we manage pH. But this is a solubility diagram for iron. And you can see that this is solid iron up here in this above polygon. And this is iron in solution. And as we increase pH going along the bottom down here, we rapidly decrease in soluble iron and increase in more and more solid iron in the system. And so we can see that as we get into higher pHs, we have solubility issues with some of our minerals, and we'll cover those a little bit more in detail. We measure pH very similarly that we would do in for salinity. We have an electrode that determines the flow of hydrogen from inside the probe into the solution, and that creates a voltage, and we convert that voltage then to the pH of the system. But that maybe gives you a little overview of what salinity and pH actually are, and why the scales are that they are, and how we can go about using them to give us an idea of what the soil condition is for plant growth. In the next presentation, which we'll follow along right here presently, we'll talk about how salinity and pH affect the availability of various plant nutrients. But while we've got just a couple of minutes here, it looks like a lot of them got answered as we went along. Thanks to my additional moderators for helping with that.
So Grant, there was a question, and I said you would answer it better.
So what was that?
Disappeared, and that was that using an in-field EC meter with using probes versus a lab. When would you use one versus the other? So
right.
Can you? Yeah, you can see the answer that I presented there, can't you? Or not?
I can see the ones that say that they were answered, but I don't see the response, but that's okay. Let me just quickly mention in reference to that. Field measurements are great, but the one thing that happens with a field measurement is oftentimes we don't mix up the solution or the soil to the proper level, so that we don't get the optimal amount of dissolution of the salts and the ability of the probe to properly measure things. We can get a good ballpark value in the field if we're careful. The laboratory has very specific levels of water that's put into the sample, and time that it's allowed to sit and dissolve salts into the solution, and those kinds of things. And so what you're going to get in a laboratory measure is a very standard procedure that will give you repeatable results, and the results that are generally referenced in terms of the tolerance of plants to those different situations. So a lot of times we'll use field measurements quickly to get a good ballpark idea of where we're at in the scale, and whether or not we think we'll have a problem that needs a little bit more detailed measurement in the laboratory. But we will rely on laboratory measurements to really give us the reproducible and repeatable reference points for determining tolerance and remedial conditions in those. I hope that answered the question well enough there for you. There's a few things here in the chat. Let me just run over to the chat. Oh, they're just responses to recordings and appreciation. Thank you.